And we are back. So I took a nice little break, had a cup of coffee. Here we are, charging forward through chapter 6, on to section 6.4. So we've got our sine and cosine functions. I mean, we also have tangent and cotangent and all that, but in this section, we're just going to focus on sine and cosine, the two most fundamental ones, and we're going to look at their graphs and properties of the graphs. Okay, so what we want to be able to do is graph the sine function and also be able to graph anything of this sort of form. And in our graphical transformations, notice that this A is some sort of vertical stretch or compression, and this omega is some sort of horizontal stretch or compression. Stretch or compression. So we want to understand how vertical and horizontal stretching affects the graphs of sine and cosine. We also want to determine what's called the amplitude and the period of these sinusoidal functions. Anything that's of the form sine of something or cosine of something is called a sinusoidal function. Period we understand is how long it takes to repeat itself, and we know that for sine and cosine that's 2 pi, but once we start changing the functions, the periods might change as well. Amplitude refers to how big it can get, and we know for sine and cosine that's 1 to -1, but again, once we start changing the functions, that might change. Then we want to know how to graph sinusoidal functions and find equations for them. Okay, so basically what we want to graph are traditional functions like the sine of the argument, and instead of calling it theta or t, if we want to be able to plug it into our calculator nicely or graph it with a computer, we typically call this just sine of x. And then how do we graph a function? We make that the y coordinate. Okay. We could also graph something like y equals cosine of x. Now don't get confused with thinking this means the cosine is the y coordinate of the point on the circle. It's not. We're just drawing a new graph. What we're really saying is, as you move around the circle, if I make this axis represent my angle, which I'm going to call x, then I can make this axis be my cosine, which I'm going to graph as my y coordinate y. Down in the unit circle, cosine is still keeping track of the x coordinate. It's just whatever that x coordinate is, I'm going to graph as a height in this graph. Okay, so we'll see exactly how this plays out. Okay, so here is the graph of the sine function. So let's see what's going on. Okay, so here's my basic unit circle. I start at an angle of 0. What's my height? My height is 0. By the time I have marked off an angle of pi over 6, my height is 1/2. So as I move down the angle axis here, which is my input argument x, by the time my angle has reached pi over 6, the value of the sine function has reached 1/2. If I keep rotating this way, what happens to the angle? It's increasing towards pi over 2. So I want to see what happens as the angle goes to pi over 2. Well, the sine of the angle goes up to 1. So let me clear out these marks so I can draw some fresh ones. As the angle goes from 0 to pi over 2, the height goes from 0 to 1, and it does so along this curve. Okay. Now back in the unit circle, what happens as the angle goes from pi over 2 to pi? The height decreases from 1 down to 0, like this. As the angle goes towards 3 pi over 2, the height decreases down to -1. So as the angle goes towards 3 pi over 2, the height of the point on the circle goes down to -1. And then as I come back around towards 2 pi, the height of the point on the circle is increasing back towards 0, and now it's going to start repeating the same picture over and over again because it's periodic. Okay. So remember, the domain is all real numbers. The range is everything from plus or minus 1, including. Okay, we went over this in the previous section. It's an odd function, so it has symmetry around the origin. It's periodic with period 2 pi. We've already found the intercepts. Okay, where is the sine of something equal to 0? At multiples of pi. We addressed this when we were trying to figure out the domain of the cotangent and cosecant functions. The biggest value it ever gets is 1. Where is the sine function 1? Whenever the angle is pointing straight up here, that's going to be pi over 2 But then I can do plus 2 pi, that's 5 pi over 2, plus 2 pi again, that's 9 pi over 2, or minus 2 pi. And where do I hit a height of minus 1? At an angle of negative pi over 2, because I could be pointing straight down like this. But then I can also do plus pi over 2 or minus pi over 2, so I get a whole bunch of solutions here. Okay. So try to graph y equals 3 times the sine of x using transformations. Use the graph to determine the domain and range. Great. So let's start with what we know how to graph. Y equals the sine of x. I know it basically does this. It takes 2 pi to do it, and then it's just going to repeat over and over and over again. Okay. I also know it starts at a height with a maximum height of 1 and a minimum of minus 1. So what's the only transformation we need to do to this? We need to vertically stretch it by a factor of 3. And that does not change any of the intercepts. Okay, so all of these intercepts stay exactly the same. But now instead of going up to a height of 1, it's going to get 3 times as big. So my intercepts are the same, but everything just goes 3 times as big. So it'll look something like this. Everything is being vertically stretched by a factor of 3. So here's the graph of 3 times sine x. So what's the domain? It's still all real numbers, because I can plug that into the sine function, and then I can multiply by 3. But the range has changed. The original sine function can go between -1 and 1, but now I'm multiplying by 3, so I can go between -3 and 3. Okay, so let me erase my picture so that we can see the book's much nicer picture. Okay, so there's the sine curve, and then you multiply it by 3. And indeed, the domain is everything, because the sine function was fine, and then we multiply it by 3. And the range now goes from -3 to 3. Okay, how about this one? -2 times the sine of 2x. So let's do this in several steps. So let me start with our generic sine curve. That just looks like this. Okay, it goes to a maximum of 1 and a minimum of -1, and it takes a length of 2 pi to complete its full little cycle. We have a couple of options of what to do next. Let's just do the -2. So basically, I'm going to take the same picture. It gets stretched by 2 and flipped. So instead of going up to 1 to begin with, it's going to go down to -2 to begin with. So it's twice as big, but it's also been reflected across the x-axis. It still takes 2 pi to finish because we haven't changed any of the intercepts. What we have is we've made it gone twice as big, but also it's switched positive versus negative. And now, finally, what happens if I put a 2 in here? That is a horizontal compression. So I take the same picture, but instead of completing after a length of 2 pi, it completes in half the length. So it only takes a length of pi to complete one full period. I'm sorry this ended up kind of tilted. I'm not a very good drawer. Okay, so that should be our picture there. What's the domain and range? It's still all real numbers for the domain, okay, because I can plug anything into sine, which means I can multiply a number by 2 and then plug it in, and that's never going to be an issue. What about the range? So here is a common error that people would make. They'd say the original sine had a range of the sine of something goes from -1 to 1. So let's multiply by -2, and they'd say, great, so 2 is less than or equal to the sine of something is less than or equal to, less than or equal to -2 times the sine of something is less than or equal to -2. This is an error because now I've somehow said that 2 is less than -2. Remember, if you multiply an inequality by -2, you've got to flip it. So since the sine of something is trapped between 1 and -1, if I multiply it by -2, I would have to flip all the inequalities. 2 is bigger than or equal to -2 times the sine of something is bigger than or equal to -2. So the range is from -2 to 2. And let's see the book's nicer way of presenting this. So There is, okay, they did it in 2 steps. They flipped it, and then they did the vertical stretch. And then they did the horizontal compression. But again, notice that the period is pi. I think it's easier to see by going out to here. That's how I had labeled it. But the period is only pi. Because we compressed it horizontally by a factor of 2, we made it go twice as fast. Okay, but there's the domain, all real numbers, and the range, -2 to 2. Okay, let's move on and talk about the graph of the cosine function. So here is my standard unit circle. Now, as the angle goes through the first quadrant, what happens to the x-coordinate? The x-coordinate starts at 1 and then decreases towards 0. So I'm going to plot that as my height on the graph. It starts at 1 and decreases towards 0. In the second quadrant, the x-coordinate was 0 and goes to -1. So the height of my graph goes from 0 down to -1. In the third quadrant, my x-coordinate was -1 and goes back to 0, so the height of my graph goes from -1 back to 0. And in the fourth quadrant, my x-coordinate goes from 0 to 1, so the height of my graph goes from 0 to 1. So there's a picture of the cosine curve, and now it just starts repeating itself. Okay. Alternately, as they've done over here, we do have this sort of table of values. So for a given value of x, I know what the cosine is, so just start plotting these points down, and they connect in this manner. Rather than link together 9 different points, I think it's nicer to actually look at the point, rotate around the circle, and just sort of see how that goes. So there's a nice little video on YouTube that I'll actually just show in here. Let me bring it over to this window so that you can see it. Okay, so as the point goes around, so the angle is being marked off. The x-coordinate is that green thing there, and the y-coordinate is that red thing there. Okay, so notice as I go around the circle, starting at the beginning, the x-coordinate is 1, and now decreasing to 0, and decreasing to -1. And as I keep going, the x-coordinate now starts coming back up to 0, and then going up to 1. And if we pay attention to the y-coordinate, at the beginning, it starts going up, and now it's coming back down as we rotate around the circle. Okay. And now, as I keep rotating, the y-coordinate is going to come back up. There's actually a Wikipedia page that has a nice diagram as well. As I rotate around, the red is marking off the height, and the blue is marking off the x-coordinate. The blue is the cosine, the red is the sine. Let me zoom in a bit. Open image in new tab. Sure, good enough. So yes, as we're rotating around the circle, my x-coordinate is being marked off in blue, and the y-coordinate is being marked off in red. So these little animations can be found all over the web. The web, I feel so old. The internet. And yeah, so these might help you understand where these pictures are coming from. Okay, so back to the book. So here we have our graph of cosine. That's good. Properties. Domain is everything and ranges from -1 to 1. We already knew that. It's an even function, a different sort of symmetry than the sine curve. It's periodic with period 2 pi, and we did already find its intercepts, and we know where its maximum and minimum occur. So here is that. Where do the intercepts happen? Where is the x-coordinate 0? At pi over 2 and its multiples here. Where is the x-coordinate as big as possible at an angle of 0 and its multiples? Where is the x-coordinate as small as possible at -pi and its rotations by 2 pi? So you can hit maximums at, that's wrong, at 0, 2 pi, 4 pi, 6 pi, etc. And you can hit minimums at pi, 3 pi, 5 pi. So your maxes occur at even times pi, and your mins occur at odd times pi, for cosine specifically. So let's try to graph 2 times the cosine of 3x. Well, we start with cosine, and let's start with that 2. So everything gets stretched vertically. So instead of being trapped between a height of 1 and -1, we're now trapped between a height of 2 and -2. But we haven't changed the intercepts, and we haven't changed the period. Next, however, comes the horizontal compression. That does not change the height, but it definitely changes how long it takes to repeat. Okay, so here I went from x equals 0 to x equals 2 pi. Since I'm compressing it by a factor of 1/3, I only need to go out to x equals 1/3 as far in order to complete the entire picture. The domain is still everything, and the range is between 2 and -2, but the period has been shortened, so the period is just 2 pi over 3. Okay. You can, yeah, so this is just showing the period of the stretched one that we just drew compared to the original. So it's twice as big, that's fine. In the time that it takes the cosine curve to do one complete picture, how many complete cycles has this one done? 1 of them, 2 of them, 3 of them. It's going 3 times as fast. So in the same length of time it took the original cosine to do 1 period, this one has managed to do 3. Okay, so we'll stop this one here. We're going to keep working through this section. We're going to look more generally at what happens, what's a relationship between sine and cosine, and more general, what are called sinusoidal graphs.